Alright, on to section 9.3. So a new type of differential equation. These are separable differential equations. So a separable equation is a first-order differential equation in which the expression for dy dx can be factored as a function of x times a function of y. So it has the form dy dx equals g of x times f of y. Okay, so we can split up the x's and the y's, and this is going to allow us to then solve it because we can split it into the x and y components. So what we're going to do, the trick to this is we're going to rewrite h of y is 1 over f of y, and that's assuming that f of y is not 0, because that would cause a problem. But we can rewrite this as dy over dx. That is g of x over h of y, because, again, h of y is just the reciprocal of f of y. Now, why would we do this? Well, because now we can cross multiply. So we're going to rewrite this as a differential. So if you remember that from Calc 1, it's where we can split up the dy and the dx from each other and look at them as separate components. So the dx is going to come over here, and the h of y is going to come over here. So this is going to leave us with h of y dy equals g of x dx. And once we have the variables separated, so the y's on one side and the x's on the other, we can integrate. So this is going to give us the integral of h of y dy equals the integral of g of x dx. Okay, and it doesn't matter what integral, what variable we're integrating with respect to, we can still compute them the same way. And then that allows us to solve for y. Sometimes you can solve for it explicitly, sometimes it's just implicitly, right? So you might not be able to get y equals some function of x every time, but that's okay. So let's go ahead and look at an example. So solve this differential equation, and then we'll find we'll solve the initial value problem as well. So part A. Okay, so to solve this differential equation, I'm going to cross multiply. So that's going to give us y squared dy equals x squared dx. Integrate both sides. So integral y squared dy equals integral x squared dx. Okay, so this gives us 1/3 y cubed equals 1/3 x cubed plus c. Multiply the 3 across to get rid of that 1/3, so that's y cubed equals x cubed plus, now it would be 3c, but because c is purely arbitrary, 3c and c, like, it doesn't matter. You can call it something else. In the book they call it like k, but because it's arbitrary, the c just kind of absorbs the 3, because it didn't matter what c was to begin with, so the fact that we're multiplying it by 3, it doesn't matter. Okay, and then solve for y, so take the cube root. So we get y equals cube root of x cubed plus c. And that is our solution to this separable differential equation. That's our general solution, because now we can solve the initial value problem. Okay, so plug in the point 0, 2. So that's going to give us 2 equals cube root of 0 cubed plus c. So 2 equals the cube root of c. So c equals 8. So in this specific case, we have y equals the cube root of x cubed plus 8. So that is the solution of this differential equation that specifically satisfies that initial condition. Okay. Let's look at another one. So let's solve this differential equation. So again, notice the separability of this. So we have the y's here, the x's here. It won't always be this straightforward, but we are just getting started with this. So let's go ahead and cross multiply. So this is going to give us 2y plus cosine y dy equals 6x squared dx. Okay, and then integrate both sides. That gives us y squared plus sine of y equals 2x cubed plus c. And we don't need the arbitrary constant on both sides. We just need one because it encompasses all of them, all the possible additional values. And this, we really can't do anything else with because notice you have the y squared term and the sine of y. You can't get one y by itself. So this one we are going to leave solution defined implicitly. Okay, so we're not going to have an explicit solution here of y equals some function of x. We're just going to leave it like that. And that is our general solution to this differential equation. Okay. So let's look at the last example here. So to solve this one, it's written currently as y prime, so let's rewrite it as dy dx, because in order for it to be recognized as separable, we do need to be able to separate out the different variables. So let's go ahead and this time notice we don't have x squared over y, it's times y, so I'm going to multiply the dx over here and I'm going to divide the y over to this side. So that gives us dy over y equals x squared dx. And now we integrate. Okay, so on the left-hand side, integral of 1 over y dy, that's going to be ln of absolute value of y. And then on the right-hand side, we have 1/3 x cubed plus c. Now this one is defined implicitly, but we can define it explicitly. Okay, so this is defined implicitly. But we can define explicitly. Okay, so and the way that we do that is we need to get rid of the ln. So we need to go ahead and raise it into the e power. Okay, so this is going to be e to the ln of absolute value of y, which is just the absolute value of y, equals e to the 1/3 x cubed plus c. And then this one, we can rewrite this using the properties of exponents. So this would be e to the 1/3 x cubed times e to the c. Because again, with those exponent properties, when you add the powers, that's the same thing as multiplying the bases. So we're going to get y equals plus or minus, because we got rid of the absolute value, e to the c times e to the 1/3 x cubed. And then what we're going to do is for this e to the c term, we're going to let a equal to e to the c, or a equal negative e to the c. be arbitrary. So we're basically just replacing the arbitrary constant e to the c with a. Okay, and so that's just a naming thing. It doesn't change anything about the problem. We're just calling it something to help simplify the problem a little bit. So the general solution is going to be y equals a e to the 1/3 x cubed.